In this video, we're going to talk about how we represent organic structures. Most typically, we use what's called skeletal structures or line structures to represent our organic molecules. An example of a skeletal or line structure is shown over here on the left. You can see the corresponding Lewis structure over on the right. So what's interesting about the skeletal structure is that it's a way for us to draw out something that represents where all the carbons and hydrogens are, but in a quicker way. I like to say that organic chemists are lazy because we don't like drawing out all those hydrogens and carbons. What we do is we assume that the ends, as well as these little bends, all represent carbons. Each carbon then has to have enough hydrogens so it has its 4 bonds. So this carbon on the left here represents that carbon on the right there. And you'll see that that carbon has 1 bond, so the other 3 bonds have to be hydrogens to get it to 4 bonds. Carbon down here in green is the same as that one in green on the right. That carbon has 1, 2 bonds, so the other 2 bonds have to be hydrogens. Okay, this carbon here is that carbon there. This carbon also has 1, 2 bonds, so the other 2 bonds have to be hydrogens. This carbon here is that carbon in blue there. The carbon that I've circled in blue has 1, 2, 3 bonds, so it only has 1 other hydrogen. That carbon there I've circled in red is this carbon over here in red on the right. That carbon has 1, 2, 3 bonds, so the other bond, the 4th bond, has to be a hydrogen. This carbon here is that carbon there. The carbon has 1, 2 bonds, so the other 2 have to be hydrogens, as shown over here on the right. And we also have a carbon right here that corresponds to this carbon on the right there. It only has 1 bond, so the other 3 have to be hydrogens. So as I said, the skeletal or line structures do not explicitly show the carbons. Also, the hydrogen atoms that are bonded to the carbons are not explicitly shown. We assume that there are enough hydrogens attached to each carbon so that it has its 4 bonds. You can see the numbers in purple here that correlate to each of the carbon atoms. So we have 7 carbons on the left and 7 carbons on the right. What we're going to do here is take this condensed structure shown here and convert it to a Lewis structure, a Kekulé structure, and a skeletal structure. And I apologize for my pronunciation of Kekulé. It's a German word and I'm probably butchering it. The Kekulé structure is essentially just a Lewis structure, but without all of the lone pairs drawn in. And you'll notice that organic chemists tend to do that a lot. We'll just draw out a molecule and not always explicitly draw out the lone pairs. So that's what that Kekulé structure is. The skeletal structure can have lone pairs or not. It's up to you. I just recommend that you're consistent. Either put on all of the lone pairs or leave them all off. So pause the video and give this a try. And if you're totally lost, that's okay. You can just keep watching the video and maybe give the next one a try on your own before I go over that one. Okay, so first we're going to start off with the CH3. I'm going to draw that out. And then we have a CH. And then a Br. And then a CH2, and hopefully you're noticing that something looks a little funny here. This carbon over here in blue does not have an octet, and this bromine over here has 2 bonds. So what that means, because we don't want the bromine to be attached to 2 things, is we just want the bromine to be attached to the blue carbon, and we want the green carbon here to be attached to the blue carbon as well. So let's do that. So here's the bromine. And now we can draw in green carbon. And our next carbon would be red. And finally, we have an NH3+. The only thing we're missing here are the lone pairs on the bromine. So that would be your Lewis structure. The Kekulé structure is going to look exactly the same, except it won't have lone pairs on the bromine. Okay, so what about our skeletal structure? Our skeletal structure is going to have 1, 2, 3, 4 carbons with the bromine attached to carbon 2 and the nitrogen attached to carbon 4. Let's draw that out. So red carbon is here, blue carbon is here, green carbon is here, and the second red carbon is there. As I mentioned before, you don't need the lone pairs on the bromine, but if you want to draw them in, that's okay too. Let's go through our next example. Again, I recommend that you pause the video right now and give this a try on your own. And then if you finish, or if you just get stuck, come back to the video. So again, we're going to start over on the left here. Okay, and our next carbon is going to be blue. And then we'll make this one green. Hopefully you're noticing as we're moving along here that on the left something looks a little funny. Neither of those carbons, the red and the blue, have an octet. So let's throw in a double bond. And now they're much happier. Okay, let's proceed. How about our oxygen? So hopefully you've again spotted something that looks very unhappy. We have green carbon over here that doesn't have an octet. So let's try and see if we can have the oxygen just attached to green carbon and if that'll help things out. Okay, that's looking a little bit better, but we still don't have an octet. Let's do what we did before and throw in a double bond. Almost there. How about a couple lone pairs in the oxygen? Okay, that's much better. Now green carbon has its octet, and so does the oxygen there. Let's keep going. Okay, so now we have a carbon here. And now we have this funky thing with parentheses. That means that we have 3 CH3 groups. So they're all going to be attached to that blue carbon. Okay, so those 3 CH3 groups are attached to blue carbon. Let's clean that up a little bit as we draw out the Kekulé structure. And remember that in the Kekulé structure, the only thing that's different really is we don't put in those lone pairs on the oxygen. Okay, so I cleaned that up a little bit, and hopefully you can see a little bit better what that Kekulé structure looks like. Now let's do the skeletal structure. We have the red CH2 right there, blue CH right there, green carbon here, red carbon here. This one's the blue carbon, and then those CH3s at the end are the ones I've just circled in green. So that would be our skeletal structure. One common question I get asked, is it okay to draw the structure upside down or have the angles a little bit different or backwards? And that's all totally fine. It doesn't matter as long as you've gotten all of the carbons and hydrogens and everything else where it needs to be. Here's our last example. And again, please pause the video and try to give this one a try on your own. Okay, let's give this a try. So we have this H3CO group, and there happens to be 2 of them. So let's see what that looks like. So there's one H3CO group, and we need another one. So that is going to be attached to blue carbon here. Okay, so this is one H3CO group, and here's the second one. They're both attached to that blue carbon. Next, we have a CH2 group, and we actually have 3 of them. If you look at blue carbon, we can't have all 3 of them attached to that carbon or it's going to have 6 bonds. So instead what this means is that those CH2s are going to be in a row. 1, 2, and 3 CH2s in a row. We have another CH. And then finally we have an O. The O is obviously not attached to the hydrogen. That would be bad because that would give our hydrogen 2 bonds. So we're going to attach it to the carbon. Pink carbon doesn't have an octet, and neither does oxygen. So let's add in a double bond. And now all we need are lone pairs on all of our oxygens. And there we have our Lewis structure. Our Kekulé structure would again look very similar. Just we'd go ahead and skip all of the lone pairs. So there's our Kekulé structure. And lastly, let's do our skeletal structure. Okay, so here's one of the OCH3s. Here's the other. There's the blue CH. And we have 1, 2, 3 CH2s. There's a CH. And then that's our last O. If you want to draw out your hydrogen here, that's totally fine. Sometimes organic chemists choose to draw on that hydrogen. Another common thing that you might see is instead of the little line on the end, because some people don't like it and think it looks a little funny, you might see that CH3 drawn out. So that's another common thing that you might see. I've even occasionally seen an Me instead of a CH3, and as we'll learn when we talk about nomenclature, Me equals methyl, which is the same thing as a CH3 group. So that's another common abbreviation you might see. Hopefully these examples give you a good idea of how we represent organic structures. You definitely want to make sure that you can take a condensed structure and convert it to a Lewis structure. That is something that you will see on your midterm. And you also want to get really good at converting the Lewis structures to the skeletal structures and vice versa. We're going to start using skeletal structures to represent what we're doing in organic chemistry. And so if you don't know what that means in terms of Lewis structure, you're going to really struggle. If you have any questions about what we did in this video, please be sure to ask me.